These are some questions I teased a bit in the chapter intro lab and things for you to keep in mind as you watch this, but we won't really get into their answers until next lesson. Do take a guess at why we might do this though, then go ahead and grab your reference tables. Let's say I have a beaker of pure water. We can describe by its makeup, that's only a bunch of molecules made from one oxygen and two hydrogens at a time. We can list its density, or its melting and freezing point, or its boiling point, which are things people know about water. What if we added salt to the water though? Does it still count as water, and can we treat it as such? Does it have the same properties? Well, it's not plain water anymore, so we have to treat it differently, and we can't expect the solution to act exactly the same way as the pure solvent. Why does salt dissolve though? And why didn't the styrofoam Frankenstein head dissolve in class, at least until I poured acetone all over it? The answer is because of the charges written here, with a somewhat negative oxygen and somewhat positive hydrogens in the water molecule, as well as the positive sodium and negative chlorines in the salt crystal. What do we know about oppositely charged things? What will happen when charged parts of water and charged parts of salt get near each other? And what will it mean for the structure of a salt crystal? We're going to find out, and it will explain these things that we call electrolytes.
Sodium chloride crystals are held together by attractive forces between the positively charged sodium and negatively charged chloride ions. When a crystal of sodium chloride is placed into water, the hydrogen ends of polar water molecules attract the negatively charged chloride ions and gradually surround them. Likewise, the oxygen ends of water molecules are attracted to and surround the positively charged sodium ions. The hydrated ions drift away into the solution, allowing new water molecules to surround newly exposed ions. Gradually, the entire crystal dissociates into solution.
Molecule-ion attractions are what the name sounds like. It's a molecule attracting an ion. In the case of that animation, it's the charged ends of the water molecules attracting and pulling on the charged ion pieces of the salt crystal. Water dissolves ionic compounds because the isolated charges on water rip the oppositely charged parts of an ionic compound away from each other. Ionic compounds dissolve so well because they actually break down into the small little pieces of the compound. Water is a polar molecule, so its more negative oxygen end, where the extra electrons hang out, will surround the positive sodium ions in the salt, while the more positive hydrogen end of water molecules surround the negative chlorine ions in salt. We call this dissociating, when a molecule breaks apart by having its pieces picked off one at a time. Ionic compounds conduct electricity in a liquid phase or when dissolved because they have mobile charges like the electrons on metal. Their ions can move freely and carry charge. By definition, molecules made from oppositely charged pieces that split apart in water are called electrolytes. When you hear ads saying Gatorade replaces your electrolytes, it's because you lose the ions in your sweat and need them to conduct charges in your body. I'm circling this phrase mobile charged particles because that's what I want you to remember about electrolytes. The opposite of electrolytes, molecules that don't dissociate in water, are called non-electrolytes. These molecules stay as one piece and don't break down further, so they don't conduct electricity well. In this picture, the salt molecule is an electrolyte and splits apart into its charged pieces, the positive sodium ion and the negative chlorine ion. Sugar, on the other hand, is a covalent compound without charged pieces, so it stays intact and doesn't split apart in water, making it a non-electrolyte. So how are we supposed to know if a molecule is an electrolyte or a non-electrolyte? Well, there are a few things to look for. The first thing to look for is if the compound is ionic. If a molecule has a polyatomic ion or is a metal-non-metal combo, that's an electrolyte. This is because it's made of charged parts that will be attracted by polar water molecules. The other thing to look for is whether a compound is an acid or a base. We'll learn about these things next chapter, but acids and bases are listed on tables K and L in your reference tables. Acid formulas are usually written with an H followed by a nonmetal or polyatomic ion, like HCl, HNO3, or H2SO4 on table K, and base formulas typically have a metal with an OH, like the NaOH, KOH, and CaOH2 bases listed on table L. You don't need to remember any specific ones, just look to see if they're listed on tables K and L. If a compound isn't there and it's not an ionic compound, then it is not an electrolyte. Covalent compounds, especially sugars made from carbons, hydrogens, and oxygens, are non-electrolytes. Whereas a salt molecule, NaCl, will split apart into the Na and Cl pieces, this sugar written here, C6H12O6, will not break down to the individual carbon, hydrogen, and oxygen pieces. It stays intact as one molecule. And don't be fooled by decoys that try to trick you, like alcohols. These look like bases because they have OHs, but the OH is with a carbon compound that looks like sugar and not with a metal. Let's try to identify some molecules. To be an electrolyte, HCl has to be either an ionic compound, an acid, or a base. It's made of two nonmetals, H and Cl, so it's not ionic. However, it is listed on table K as an acid, so that does make it an electrolyte. You can abbreviate this E if you want to. The Y is because it's an acid. And when it splits apart, it separates into the H plus and Cl minus pieces, so it produces two ions in solution. C6H12O6 is not an ionic compound since it's all nonmetals, and not listed on the acid or base charts, tables K and L, so it's not an electrolyte, or a non-electrolyte. It's a sugar. It stays as one piece in solution. So those C6H12O6 pieces do not break apart. It stays as that one molecule and won't get smaller than that. It just stays as one whole chunk. NaOH is on table L as a base, so it is an electrolyte. And like HCl, when it splits apart, it will release multiple pieces. The Na plus ion will split apart from the OH minus ion. I don't know what's with my pen that this is freaking out right now, but that's not good. ZnCl2, zinc chloride, is a metal and non-metal ionic compound, so it is an electrolyte. I'm just going to abbreviate it as E because I don't feel like writing that whole letter with this pen that's acting weirdly. When it splits or dissociates, it separates into the Zn plus 2 ion and the 2 chlorine Cl minus 2 ions. So that's 3 total ionic pieces that will be released into solution. So ZnCl2, again, it's metal and non-metal, so it's ionic. And when it splits apart, you'll have this piece right here, the Zn, separating from each of the Cl. So you get one piece here and 2 pieces there. So 3 pieces total will separate out from each other. So try the rest of these on your own, and we're almost done with this lesson. Sometimes you'll see a tricky example like this acid that doesn't look like an acid, since it doesn't start with an H. It is listed on table K though, so make sure you check tables K and L as a standard approach and you won't have any problems. Finish the form in your OneNotes, and next time we can finally find out why we put salt on sidewalks.